Hello everybody, I'm going to show you my new program that I made. This is on the first version, which is called version 2000 because it has 2000 lines of code. I'm going to make one of these videos for every 1000 lines of code that my program gains. In this first version it has 3 files with it. Okay, so the main jar file, which is the program itself. It's an executable jar file. And then it has 2 other files, one for keeping the definitions that you save and the other for keeping the theorems that you save. So let's open up the main one now, and you see you start off with this nice little screen here that is for inputting a boolean. This is the first thing that I added to it and will probably be removed soon, as it was just to test things out. So if you type in true, for instance, it'll obviously give you true because that's a boolean for true, but if you type in false, it will give out an output of false. If you put parentheses or something in, or whatever you can think of, it'll still give you a valid output. This is accomplished using definitions and storing all the different definitions within them. These definitions are stored in the definitions.ptxt file right here. This first one is simply a placeholder, as it tended not to load the very first expression. So then if it doesn't load this one, then everything should work out fine. If we open it up again, let's get this full screen here now. The second thing I want to show you is an add definition box. Okay, now in order to add definition, first you need to know how many values your definition can have. We'll create a new definition that will hold simply 1. Okay, so right here is where you define your definition. Okay, since we said it only has one variable, we'll just name the variable A, and it is a Boolean expression, or a Boolean variable. And let's call this not A, like such, with an exclamation mark before it and then the A. This will be defined, and this is a special thing. If you just put a not here, it's a not expression, so then this will just be considered whatever an A is and then not that. So if it's true, it'll be false. If it's false, it will be true. Now we just hit submit definition, and then the definition is submitted into the file. Let's exit out of this right here. Okay, now the next thing I need to show you is the add theorem. This is where most of the meat of the program is. We'll start off with something very simple and show you that if you type in true, it'll highlight it green, showing you that that's a true statement and can be done. And over here it'll show true to show you what that means. Okay, now if you type in false, that is obviously a false expression. So it'll be highlighted in an orangish yellow, and over here will display false. Okay, now if it doesn't know what you typed in, or there's a problem with it, it'll highlight it in red and put over here error. Okay, that way you know that there's something wrong with what you did. It'll also be more specific over here for other kinds of errors, so that you can more easily pinpoint what you have done. Now, let's try to prove a very basic theorem. But first, I need to show you can indeed save your own variables into this to use in the theorem. However, these are not entirely useful as of yet and are still being implemented. So if we say given x, and we say that this is an element of the set of booleans, it'll be true, of course, because it can do that. And then we say let x, and then down here is where you insert the special characters. Okay, and then this is equivalent to true. So now x is going to be a true statement, and it shows up true there. You say not x, it shows up false. So it understands the definition of x now. So now let's get to the actual meat of this and try to prove a theorem here quickly. So we're going to prove a 3 variable. So first you type out the variables that will be in your theorem and you say what they are. Okay, that way it knows what it is. So 3 variables, A, B, and C, and they're going to be all 3 Boolean expressions. You insert this special character here to separate that from your theorem, and then we're going to type in the actual theorem. So A and B in parentheses and C. We want to show that this implies A and B and C. Okay, this is probably pretty obvious to you that this would be true, but it is still important to prove it. Okay, so after this, you'll see that our theorem was correct. Not necessarily correct, but it's an appropriate theorem that we can try and solve. Why it's highlighted in green. And it shows over here what we want to prove. Okay, so we want to prove that A and B in parentheses and C implies A and B and C. Okay, so first step that we're going to do is we're going to assume the very left-hand part of this. So assume that A and B and C. Okay, now since we have assumed this, now we just want to show that A and B and C is correct. Okay, now what do we do? How do we do this? Well, we want to split this up because we know A and B and we know C, so we want to split these two up. Well, in order to do this, we have to use a theorem. Okay, so these are the different theorems that are already pre-entered. Okay, but we want to show that A and B and C. So we choose this one right here that shows that A and B is equivalent to saying A and B. Okay, so what we do is we insert this. Now the two variables that we're using for the A and B are different than what we show here. Okay, so the first variable is A and B. Okay, so then it replaces this so you can see what it's going to look like. And the other one is just simply C. So here we see on this side A and B and C, which is exactly what we have here. And this tells us A and B and C. So we're going to use it to find out this first one first. Okay, so we'll submit this. And we'll say because of this we know A and B. It says it's true because we do in fact know that. Now let's copy this and use this again to show the other side of the expression. Okay, so now we can say we know C, and it's true because we do know C. Now we want to show that A and B and C, but in order to do that we need to split up this A and B statement right here. Well, we would like to remove the parentheses from this, so we'll make it a little bit easier. So let's look in here. Now here's another trick that we can do. There's a lot of theorems to look through, and I don't know if I want to. I just want to find one that has one variable inside with parentheses, and it removes those parentheses. So what we do is we hit the variable search. We want to know how many variables it's going to have, and it's going to have just one because it's just a single variable. And the variable type is a Boolean. Okay, so we hit enter, and it's going to show us all the theorems that we have that are just one Boolean expression. Okay, so here's the one that we want. So we're going to say insert that, and the variable we want on the inside is A and B. Okay, now we hit submit, and it gives us this, and now we can say we know A and B. There we go. That is obviously true because we had it right here. We had known that. Now that's great and all that we have this, but now we want to show that we know A and we know B. Okay, so we can use the same theorem that we had up here, but we're going to have different variables this time. So I don't want to try to find this, so let's just do the variable search for two variables this time. And let's say the variables are both Booleans. Okay, now I'll show this all the two variable expressions, theorems that we have here. Okay, so now we want to find, oh there it is, right there. Okay, let's insert this. And this is exactly as we want it, A and B, and we want to show that A and B implies A and B. Okay, so we have the two A's and B's. Now let's submit this. You can see that it separates it with a colon in the middle, but you don't have to worry about that if you're using the inserter. Now we can say with this we know A, and with it we also know B. But in order to do B, you need to reverse the order of the variables, as that would be a different theorem otherwise. No. Let me try this again. So insert theorem. We want to use the same theorem here. We do not need to reverse the variables at all. Okay, there we go. There we go. Okay, so we know B as well. Now let's use these to show, we want to show that A and B and C, right? So first off we need to show that B and C is true. We can use the same theorem that we have been using, but since we know B and C already, we can say we know B and C. Okay, there, now we know B and C. Now using the same theorem up here we used to parse apart the parentheses, we can use it again, but instead of A and B inside, it's going to be B and C inside, and it's going to tell us that we know B and C. There, done. Now we need to combine this with A, and that's a very simple step. I don't feel like typing it out, so I'm going to do this insert theorem again. But our two variables now are going to be A and B and C in parentheses. Because you see that this is what we want, A and B and C. Okay, A and B and C. And what we know is we know A from up here, and we know B and C from right here. So if we submit this, and we say no, A and B and C, it'll say that we know it. And since what we know right here matches up with what we want right here, letter for letter, it gives us a proof complete. Okay, so we are done with the proof. Now that the proof is complete, we can click Build Theorem, and we're going to give this theorem a special name. We're going to call it 1.3. Naming it 1.3. Okay, you hit OK. Theorem added. Now when we hit Insert Theorem, we can see our theorem 1.3 is down here, and we can then use it to prove new theorems as we see fit. Some things that I wish I could add to this but are not added yet as of version 1 with 2,000 lines of code is there is no way currently of proving an if and only if statement, only an implies statement. What could be done is you prove two theorems and then combine them in some way, or it is also possible that we could have two different cases. Probably the case system is going to be what is used. Anyways, also what we could do that we don't have yet is a theorem. Say if we say theorem a Boolean, and then we insert the theorem separator, and we say A implies A. We do not have a way of doing this without using a previous theorem. Okay, but what could be done that would make this a ton easier is if we could do something like by definition and say A, change all of the A's in parentheses to A's. But we can't do that, as we don't know, I don't have that programmed in yet. But soon you'll be able to do that, and then that will just replace for the want that A implies A, and then you can just say assume A, and then what you want matches up with what you know, and then you would be done. So it'd be a really easy theorem to prove. And this would also come in valuable for other theorems where you have parentheses and you want to get rid of them, like in the previous theorem I showed you. Okay, I'm going to show you one more feature, and then that'll be it for this video. Okay, so the next feature I'm going to show you is what's called logic. Actually, two more features: logic and contradiction. You can do proofs by contradiction with this. So first I'll show you that. So you're going to have two values, A and B, and you're going to say that these, you're going to put in the theorem separator, and then you're going to say A and B implies that one of the two is true, and that's obviously true. But what you can do is say contradiction. Okay, and what that will do is it will swap this A on the right side to the left and put a knot around it, and then this left side and swap it to the right with a knot around it. That way you can use proof by contradiction for what you want to prove. And this makes it a little bit easier to prove this statement, because you can then use the A implies not A. So not A implies not A or not B, and then you can use the or separator. Another thing that you can do is what's called logic, and that just brute force goes through every single possibility, make sure every single one is true, and indeed they are. Thus it shows you the proof complete, and it shows a little end over here to know that your proof is done. Okay, so it's true, the logic is true, so it shows proof complete. Now, if the proof was not, you have to go like this to, there's a bug. Anyways, if you were to show that the proof was not complete, if the proof wasn't true and you used logic, it would just simply say false. If you can't use logic for it, the logic will return an error, knowing that you need to indeed prove it. So that concludes what I have to show you about my theorem so far in this video, and I can't wait to make my next video for the 3,000 lines of code, and that one will be a lot better. So I'll see you then. Have fun as always, and goodbye.